So now let's look at example 2. The GRE is an exam that you want to take before you get into graduate school. It's essentially the SATs, but for graduates, graduate school, if you will. I believe it's actually made by the same company that makes the SATs. But anyway, it has, suppose it's normally distributed, because they designed those tests that way generally, with a mean of 1066 and a standard deviation of 191. Suppose n equals 15 randomly selected students take the GRE on the same day. Okay, so we're going to look at n equals 15. Now let's look here. What is the probability that a randomly selected student scores between 900 and 1200? A randomly selected student. We all passed English class at one point. That's single. That's one person. Now I drew a picture of it here, which of course you would just draw on your paper, because StatCrunch and Excel don't make these pictures nicely. But what we want to talk about is this central guy right here. So you draw the normal curve, you put 1066 right down the middle, and then you put 900 over here, 1200 over here. 1200 is on the right, 900 is on the left. That's about all you need. So we want to be able to find that central probability. All right, we're going back to Excel. Okay, so this is 8.1, example 2. And while I'm on the subject, I'm going to save this sucker. I've already labeled it technology, but I'm going to save it again. That way I've got it. All right, now central ones are the worst, but that's what we're going to have to do. So 1066, and then the standard deviation. Let me go back here real quick. This was for a single student, 1. So it's just 191. Nothing's changing when it's talking about an individual. Oops, right back here. So 191 is my standard deviation. And I want to be less than, well, I'm going to have to do it twice. I'm going to have to do 900, and I'm going to have to do 1200. So I'm going to compute 1, take a snapshot. 8.1, example 2A, part 1. Okay. And I'm going to do it again, but for, I think it was 1200 was the other number. Yep, 1200. Okay, so put 1200 right down here. Compute. There we go. Snapshot. Was this example 2A, part 2? Okay. Now I'm going to go to my StatCrunch, and I'm going to copy and paste those. Oops, that's me fiddling around with our lecture videos. StatCrunch, there we go. Okay, so let me go back to my results. There they are. Click on one, copy. We've done this a bajillion times now. Let me go back. There it is. Copy. All right. And again, we're just learning how to do both ways because that's how we're going to roll. All right, so StatCrunch. So the probability that 900 is less than X, which is less than 1200, was what we were asked. What's the chances they score between those two values? All right, so this is for n equals 1. This is talking about for an individual. All right. So then we just say, okay, that's equal to 0.7585265 minus 0.1923935, right? Because it's these values, the high one, take away the low one, and you'll have the in-between part, right? If you vacuum off this little red part past 900 over here, you're going to have nothing but the in-between. All right, so there's StatCrunch's answer. Now let's go find it with Excel. Okay, so same deal. I'm probably going to put all this in one sheet here. All right, so for Excel, we just take equals norm, dist. I'm just going to do it all at once. I want 1200 first. You take the high one minus the low one. 1066 was my mean. 191 was my standard deviation. True. Oops, and I don't want to press enter. Well, yeah. Minus norm dot dist. Now the same thing, except 900 comma 1066 comma 191 comma true. True just means it adds it up, shades the whole thing, if you will. There you go, same number. All right, so I'm going to copy and paste this in to my notes because that's the answer we were looking for, the 0.566133 blah blah blah. All right, now how does it change if we're going to start looking at samples of size 15? Instead of looking at the individuals, we're going to look at groups of size 15. What's going to happen? Okay, well, the shape is still normal because they told us originally that the population was normal. If it's normally distributed, that means when n is equal to 1, it's normally distributed. So therefore, it's still normally distributed when n is equal to 15. The center is going to stay the same. Centers don't change. It's 1066. But the spread is going to be significantly smaller. It's only 49.316. It's 191 over the square root of 15. Now, I drew both pictures here just because I wanted you to catch what was happening. Technically, only the black-gray one is what's asked for in this problem. But I just wanted to show you. See the blue one right there? That's this blue one right here. I even put the vertical lines in it and everything. See? 0.5661, which is what we just found. And you can see the answer. This is Minitab doing this, but you can see Minitab's telling us it's 0.9963. Should you totally be able to read a graph like this and know what it's telling you? Yes, you should. Right? So that's the kind of way I could ask questions like this. So sometimes I won't make you do the calculations always. Sometimes I'll just give you the picture and ask you, or give you the Excel output and ask you questions. Okay, so let's do this again. All right, we still got the 1066, but instead of 191, we want 49.316. Compute. See how high that is? See? Because there's only a tiny bit over here that's not covered. Take a snapshot. This was 8.1, example 2C, part, it doesn't really matter, part 1, part 2, fine. And then we're going to do it again, okay, with 900. Compute. See? 900 is so far over here. It's such a little bit of the tail, see? That it basically says it's 0.00038. It's scientific notation. It's really small. So compute. I'm going to take a snapshot. This is 8.1 example 2C part 2. Export. All right, so let me go here. All right, I'm going to copy and paste these in. I'll see you back here in a sec. There we go. I figured we were pretty sick of watching me do that over and over. Okay, so now I'm going to find those same things. I'm going to put them down here next to these pictures that they're with. But this is for n is equal to 15 this time, right? Okay, so and let me just make a note to myself. The standard deviation was 191, right? But the standard error is equal to 191 divided by the square root SQRT of 15. Okay, I'm going to use that later on, right? You can see I was right. It was 49.316, which is what I said it was right here. I found that with a calculator or whatever. Okay, so back to Excel. Okay, so I can take it by saying it's equal to 0.99670786. That's the one on the right, the big one, minus. Now remember what that is. That's 0.003812678.3. You got to move the decimal 4 spots to the left. So the first one takes the 3, and then you move it 3 more spaces over. Enter. All right, now if I was going to do this with Excel, same thing. It's just instead of 191, I do that cell right there, 49.316. And then this 191 needs to go away and make 49.316. Enter. Same number. Isn't that great? All right, so this is, I'm going to make it orange. There we go. I'm going to copy and paste that back into my notes. And I can see that Excel was right, or excuse me, Minitab was right. Minitab said this was 0.9963. Minitab is a wonderful program. It finds it very simply and fast, but unfortunately you don't want to have to spend the money to buy it. All right, so there we go. And again, you don't really need both graphs, but I like having both graphs there just to remind us of what's happening. All right, let's look at the next one. So in the US, the year each coin was minted is printed on the coin. So to find the age of the coin, you subtract the current year from the year printed on the coin. So for example, it's 2012 right now when I'm making this video. If I pick up a coin that was made in 2000, that's 12 years old. So its age is 12 years. So assume the ages of circulating pennies have a mean of 12.2 years and a standard deviation of 9.9 years. Okay, so based on this information, can we determine the probability that a randomly selected penny, single penny, is over 16? And the answer is No, right? We don't know the shape of the distribution, right? So as a matter of fact, no, we do. We know it's right there. See it? It's right skewed. Uh-oh. So if you know it's skewed right, or even if they didn't tell me, if they said, oh, I don't know the shape of the distribution, you need your n to be larger than 30, right? But when you're talking about a single penny, that's 1, right? So this is n equals 1. So since we know it's right skewed, we can't use our rules of probabilities, namely we can't use norm.dist. And since we can't use norm.dist, we're in trouble. Or norm.dist, if you have the old version of Excel, it's just norm.dist. Okay, so we can't do this, right? We cannot find a single probability. We could up here, right here, that blue one, that's a single student, but that's because it told us in the beginning that it was normally distributed, right? Down here, it tells us it's right skewed, so we're in trouble. We can't do this for a single one. Now, what if it was 40 pennies? That you could do. So, probability that a random sample of 40 circling pennies has a mean age greater than 16 years. Okay, so let me pull up StatCrunch right here, which I have right down here in my little Java thing, or you can go to StatCrunch and grab it here, stat. Okay, so I want, my mean is 12.2, my standard deviation. Now this is going to be a little different, okay? So I need to know the center and the spread. So the center is 12.2. The spread is not 9.9 anymore. It's 9.9 over the square root of 40. And I know it's normal, by the way, because n is 40 is bigger than 30, right? So 9.9 over the square root of 40, I found with a calculator, it's 1.565. So I'm going to, oopsie, put that away. I'm going to go type 1.565 right here, not 9.9. 9.9 was for individual pennies. Now I want us to be less than, greater than. So I can switch this to a greater than symbol and put 16 in here and click compute. And there we go. 12.2 is the center. Standard deviation, it's really the standard error, if you will, is 1.565 because it's a 9.9 over the square root of 40. I did a greater than because it wants to be older, so I switched this little symbol to a greater than. And I did 16, and then I found it. Okay, let me copy and paste that in. Hold on one second. There we go. I copied and pasted it into my notes because you really just want that picture. And I put it in Excel, of course. So let me type this up real quick. Okay, so I just typed up what we had. That in StatCrunch, it said that this was the answer, 0.007. Now for Excel, this is the one thing StatCrunch does better than Excel. I just wanted to remind you that norm.dist, okay, finds, let's see, x was 16, the mean was 12.2, the standard deviation was 1.565, comma, true. Okay, that's this white area. It finds left to area. That's all that norm.dist does. So if you want a right tail like this, you've got to do 1 minus that value. And there you go. It's the same number that StatCrunch finds. So just a reminder, norm.dist only finds left areas. It won't find right areas for you. So you have to do 1 minus the left areas in order to find the right because they're complements of each other. Remember that from chapter 5? Right. All right, so there we go. Boom. Very, very small, 0.0075 chance, which is less than 1%. So suppose you actually did get a batch that was 16 years old. What are some things you could reach? Because that's a really low chance. So you could say, hey, maybe it was a biased sample. Maybe the random sample you got was actually from somebody who's a coin collector, or I don't know, they're magic and they just hold old pennies around. Who knows? Maybe it was a fluke. Maybe it was just random chance. But the random chance probability you just found was 0.0076. Okay, so very, very low. So it's probably not likely that it's random chance. It could be a biased sample. Somebody knew you were going to do this and just brought old pennies on purpose. Right? Or it's possible that the 12.2 is totally wrong. Where did that number come from anyway? Who knows? Well, that's what we cover in chapter 10, right? How do you know that something's just suspect? Well, if the chances of it happening by accident are really, really low, then you know that it's got to be something else maybe. You don't know for sure, but you assume, maybe it's the 12.2 that's just totally wrong. All right, we're all done. I'll see you back here for 8.2.